of the difficulty, for example, that you get when you try to define the integral of some function with respect to, for example, Brownian motion, then the difficulty arises is that Brownian motion does not have finite variations actually. Okay? And after the moment that what do you mean by the finite variations? I mean, if you remember our first discussion, we talked about that if you have a continuous function, you can't even define its integral with respect to itself unless you have some additional properties in that continuous function. Okay, so leave aside the Brownian motion actually, are integrating with respect to the Brownian motion. Okay. So what we're going to do today is that, Brownian motion, for example, now what we're going to do is that Brownian motion has quadratic variations, but it doesn't have variations actually.
Sir, वो zero होगी ना?
No, they'll explode actually.
वहाँ पर हमने condition दी.
Anyway, so let me define what do we mean by quadratic variations. Okay. Start from here. So as a definition, so if I have a process X, okay, so X is process X T, where T takes, basically values in some time domain could be finite or infinite. Then by the quadratic variation of n, we mean this. So here's a symbol. So the variation, quadratic variation of the process X over the interval T, okay, evaluated at the end, so it's a discrete process actually, okay, is defined as, also denoted by identically another notation, that it's a quadratic variation of X on the dk, where dk are the instants in the interval 0 to t. Okay, and you define it as that it's a basically sum that goes from 0 to n minus 1, and you have the squares of the increments actually. Okay, so x tj plus 1 minus x of tj and everything is square actually. Okay, and if, okay, then you can treat it as that it's a partial sum actually. So the partial sum of the quadratic variations of the process actually. Okay. So what would we like to do? We would like to look at.
Sir, the index is not clear to me. The k index.
K index? Which k index?
In the x of.
Okay. So here's the thing. You can say you have this interval 0 to t, and you have broken it into some parts. You have partitioned it. So this is your t0 and t1, t2, and maybe tk minus 1 and tk actually. So this is just symbol. Okay, so you are computing the quadratic variations of the process xt. This simply means that you split your interval into some finite amount of, you partition it, and after partitioning it, you compute the increment, okay, of each of the subinterval and square them and sum them. So that's really partial sum. Now, the definition is not over. So we say, if I can find a function or a process, if we can find a process that I'm denoting xx, okay, x, such that so this is a time-dependent process. This is a time-dependent process. Okay. So that's an abstract notion for that. Okay. So what is this x-axis? That these quadratic variations are these variations, finite variations of the process x, okay, evaluated at n, converge to this what we call process xx in probability as n goes to infinity. Then you're going to say that this process x, the quadratic variation of x, is, okay, this process xx is called the quadratic variation. Of process x. So in simple language, you have a process. You are defining a sequence actually, roughly. Okay, so it's a sequence defined through a sum of the variations of the process x. Okay, and then you're saying that, you know, if this sum is converging basically, you know, as that goes to infinity to some function. So if it converges, that function is called the quadratic variation of the process x. Okay. Obviously, so in a way you can see this as, you know, such an expression that goes from j equal to 0 to infinity actually. So these are like the partial sums actually. Okay. So saying that the sequence of partial sums of the quadratic variations of the process x converge. If they converge, okay, to some process, you're going to call that process as the quadratic variation of process x. Okay. Written in a fancy language, but that's what you say. Okay, and you can need this convergence in probability. Okay. What would be simple variation? Okay, so I'm not rewriting the definition of variation, but just change everything and give it a power on it. Okay, or maybe the best would be that if you, instead of saying quadratic variation, call it pth variation actually. Okay? These are the pth variations. Okay? Of the process f, and you're going to say that this process is the pth variation of the given process x if this sequence of the partial sum converges to, you know, and obviously you have to, if you're keeping an arbitrary power, you have to keep it in absolute actually. Okay, so this to this function x. All right. So let's, you know, think about the quadratic variations of the Brownian motion. Okay, so that's one of the key things that we talk about. So here's a PA. Okay, here's a PA. So the quadratic variations for the Brownian motion, okay, evaluated at p is basically t. Okay. The quadratic variations of the Brownian motion is t, so that's what we like to. Okay. Proof. Okay. That if you compute the quadratic variations of the Brownian motion, we're going to have this motion. For that, you need to show this convergence in probability, but I know that if you want to show the convergence in probability, it is sufficient to show the convergence in L to omega, for example, for the quadratic variation, because I know that convergence in, you know, LP implies the convergence in probability. Okay. So, how can I show this convergence? So I need to take these guys, okay, and compute I need to show that this guy, as n goes to infinity, converges to the t in, for example, L2 omega, and that is going to imply the convergence in the probability. Okay? So, here's a proof. So, I'm just giving you a sketch of it, at least, for getting into more details of it. So, let's consider the variations. W of tj plus 1 minus W of tj square, and what let me talk about its, difference. Okay. I can rewrite this expression as, so in other words, I can rewrite this t as a telescopic sum actually, and I can include this increment into the sum.
Say.
Okay, so j equal to say 0 to n minus 1, and what would be that telescopic sum? Can you guess? So this obviously is going to be tj plus 1 minus tj. Okay, because we are starting from 0 and ending at.
So Tn is T.
You can explicitly write that Tn is T. Okay. So how can I show it? So what should I show? What should I do actually? So I should show that this guy converges to 0 in probability. Okay. So it's sufficient to show. And for that it is sufficient to show that this guy converges to 0 in L2 omega norm actually. Okay. So how can I show that this is going to get to the L2 omega norm? So you need to take the square of it and compute the expectation. Okay. So let me give this entire guy a name xj for example. I need to put a square of this.
Say.
Okay. So give this entire guy name xj. Okay. So what would be the expectation of xj? Simple xj. Then we'll think about the sum. So the expectation of xj is going to be expectation of this minus this. But the expectation of this is tj plus 1 minus tj, and tj plus 1 minus tj, so it should be 0. Okay. This is.
सर वहाँ पर स्क्वायर नहीं होता ना इंक्रीमेंट में, हम स्क्वायर की एक्सपेक्टेशन ले रहे हैं ना, वहाँ पर इंक्रीमेंट में स्क्वायर WTS minus WS होता है.
What is the definition of convergence?
The variance is
Every increment is normally distributed with mean zero variance
T minus S.
Okay. What is the meaning of variance? The meaning of variance is the expectation of
X square minus expectation of X.
the expectation of, because the mean is 0,
हाँ.
so the expectation of square of the WT minus WS is
the
so just look at the definition.
सही है.
variation is बराबर.
This follows from that. Okay. Now, what I would like to show? So I would like to show that if I take this xj, okay, and square it, इस पूरे सम का नाम देना चाहिए. So what should I call it? Okay. Let's have this sum. So I'm not writing this expression. We have this sum. J equal to 0. So ये एक, this is like one aside that you have to keep in head. Okay, n minus 1. And a square, and I would like to talk about its expectation. Okay. So what would be the expectation of it? So first we need to basically settle down this square. So what would be the expansion of this square? So this square is going to be sum of j equal to 0 to n minus 1
of all the
xj square,
जो भी component
right? And plus 2
I
times of a double sum,
I
which
less
is
than j.
over I and j, and you're going to say I less than j,
xj xi
xi, xj,
ये
right? And you have to compute its expectation, but the expectation is linear, so this times
this
this is what that you need. Am I going too quick? Okay. So if I am calling this entire quantity xj, so I have to square this xj, okay? And I'm just applying this sum, you know. And obviously, you have to keep it with this sum is a double sum actually. So it's a double sum. So when these indices I and j agree, so I have just have kept them here, and the rest of things are here. Okay. And then we need to compute the expectation of it, but the expectation is linear, so you know, we can have it. So let's think about this. Let's think about what would be the expectation of xj square now. So we need to square that quantity. So what would be the square of this quantity? So the square of this quantity is going to be expectation of w of tj plus 1, okay, minus w of tj raised to 4, okay,
minus
plus
minus
tj minus tj plus 1 minus tj square,
ठीक है
right?
अब माइनस का 2
and plus okay, plus or minus
minus
plus,
2 times of
2 times of
product
tj plus 1 minus tj, right? Times w of
tj
tj
plus
1 minus
w of tj
Square.
tj and
All
it's
is
square actually. So you have it. And so this would be same. So this is like a number, so it's going to come out of expectation. So this is expectation actually. But I know that this is zero. Expectation of xj is 0. Would that be? No. It's not going to be 0.
Tj minus plus 1 will be.
It's not going to be 0. Tj plus 1 minus tj and
That's expectation of
this guy.
This would be, sir, equal to Tj plus 1 minus Tj.
Yes, so
One term would be
square actually. So you're going to have a minus tj plus
minus Tj plus.
Okay. So what would be this? Now I'm just recalling your fact. You may check it for yourself. That if you have a random variable that is normally distributed with mean mu and sigma square, okay, y that is normally distributed, then the expectation of y power 4, okay, is basically 3 times of sigma power 4. By the way, it's not a difficult thing to figure out this formula y, because you know the moment generating function for the normal random variable actually. So okay, you can differentiate it 4 times and substitute t equal to 0. You're going to see that this is something that you're going to get actually. Okay. So keeping into this, what would be the outcome? So the outcome of this is going to be, so how this is normally distributed?
0 and
4 here. So it's tj plus 1 minus tj. So this is the I think we should put a square here and a square here. नहीं, फिर वैसा भी हो जाए, वैसा भी हो जाए, वैसा भी हो, still, ठीक है, so you have it. So I know the distribution of this, that this is normally distributed with mean 0 and tj plus 1 minus tj. Okay. So as per this formula, this first expression is going to be
3 times
3 times of
tj plus 1
so tj
plus 1 minus tj
plus 1 minus
tj power 4
tj power
4
4
Square.
tj power 4, yes.
Square.
Eq square.
वेरिएंस जो है ना वो टीजे प्लस 1 माइनस टीजे है, उसमें वेरिएंस है सिग्मा स्क्वायर, वेरिएंस को स्क्वायर
Yes.
है।
Okay, so this will be square. So it's going to be square. And what you have from here, so if you simplify it, this is tj plus 1 minus tj square. Okay, so what do you get? You get 2 times of tj plus 1 minus tj, and this is square. Okay? So I'm writing a direct argument. I can estimate this guy by 3 times of tj plus 1 minus tj times maximum. Okay? Maximum of tk plus 1 minus tk, where k could be anything between 0 to n. Okay, or maybe 0 to n minus. Can you see this mess? नजर आ रहा है? नहीं नजर आ रहा. So are we happy with this? 2tj plus tj, minus 1 square, right? So 2 times of some tj plus 1 minus tj. So I want to estimate it. So I have a square it. So I'm keeping one power and the other, factor tj plus 1, I'm estimating by the maximum of the all increments that you have. Right? Here k is anything between 0 to n minus 1. Can you see it? Okay. And my point is, this will go to 0 as n goes to infinity. This will go to 0 as n goes to infinity. Why this will go to 0 as n goes to infinity? So in other words, you are making your mesh more and more and more and more and more fine. Okay? Then this maximum, each subinterval, and hence this maximum will tend to 0. Okay? And if the maximum tends to 0, that means that all of the subintervals, their lengths are going to the 0. So this will go to 0 for sure. Okay? So what does this calculation shows? That, in this expectation, this guy goes to 0. Okay? This guy goes to 0 and then goes to infinity. Okay. The next thing is this. This is easy peasy. 50. So I is less than j. So where can be I? So I have I minus 1 and say I is here, and j can be either equal to I, nahi. Too quick. If I is, I mean, ठीक ठीक है. So I somewhere here and J somewhere here. Okay. So I know that I minus 1 is an instant here. So where could be J minus 1? So you have the two possibilities for J minus 1.
या तो I के ऊपर
So either J minus 1 is going to be here, or in the worst case is going to be here. Okay. So in both cases you are away from this part.
independence.
Okay. Now if you compute the increment of the Brownian motion in this interval and compute the increment of the Brownian motion either over this interval or this interval, no matter what case it is, these increments must be independent actually. Okay? And xi and xj are something that depends on the increments of the Brownian motion. Okay? So they must also be independent. Okay? So if they are independent, what will happen? The expectation of xi times expectation of xj would be the expectation of xi times expectation of xj. And what is expectation of xi? You see that this also goes to 0. Okay? So what is the net conclusion? The net conclusion is that this converges to these quadratic. So the difference of this partial sum and the quadratic variation that you are claiming actually goes to 0 in L2 omega. Okay. And if you have this convergence in L2 omega, this implies convergence in measure as well. Okay, so convergence in probability. Okay. So what does this property mean? So what does this property mean? So in other words, it says that if you keep on tracking, the quadratic variations, okay, of the Brownian motion, basically you will see that they will become linear actually. The quadratic variation will become linear or they're proportional to the TH. That's what it says. Okay? So it's a sketch, so just finish the proof actually. Okay? And here's an exercise for you. The exercise for you is that the variations of the Brownian motion. Okay, so if you just have j equal to 0 to n minus 1 and w of ej plus 1 minus w of ej, okay, this explodes actually as n goes to 2. The variations explode. And this is the reason, really, that you can't define the stochastic integral of a suitable function with respect to the Brownian motion in Riemann-Stieltjes sense actually. Because you need this. You need such increments to converge actually. So you don't have it. So therefore, Riemann-Stieltjes, the definition Riemann-Stieltjes,
Not sufficient.
so you can't, you just have to throw it in the bin actually. Okay? It doesn't work when you want to define the integral of something, some suitable function with respect to the Brownian motion actually. This doesn't work. I mean, if you wish, you can keep this fancy, what you call, notation in your head. Otherwise, you can just keep quadratic variations as the series, okay? So the infinite series of the quadratic variation, and by variation, just series of the variations of the Brownian motion. Okay? And by pth variation, we mean, the series of the pth powers of the variations of the process. So this is one of the interesting and key property of Brownian motion. Okay.
सर ये आपने सिंपल वेरिएशन के लिए लिखा है,
यस सिंपल वेरिएशन।
वहाँ पर तो क्वाड्रेटिक
कहाँ पर
स्टिल जी वाले केस में क्वाड्रेटिक का
still the case of simple variation. So we were trying to define
f with
f with respect